Okay, so we've got two new topics, and they're going into just barely brushing on modern physics. Um, we know that light is a wave and light contains energy. And electrons are bound inside their metals by some amount of potential energy. And it turns out when the light rays hit them, it knocks the electrons out, and we can measure those as something that we'll call a photocurrent. So let's say that we just shine a little bit of blue light on this zinc, and this is something I wish we got to do it, right? Because it loops all the way back to the very first experiment we did, where we rubbed the rabbit's fur and the PVC pipe, and we had to figure out what charge is this. You don't know, right? You need a key. All we can say is that these charges are the same or the opposite in different combinations, but how do you crack the code and figure out which one's plus and minus? So I would rub the rabbit's fur, smear it on this plate. So now I've got a lot of electrons that just are hanging out on it. And they want to get out, but they're kind of stuck by some potential energy in the metal. So as we shine a light source, and remember the light source has waves, and the waves contain energy in the electric fields, we start to see electrons pop out. And they come out with a little bit of extra kinetic energy. So we've used some of the light to buy the freedom in PE, and whatever's left over, that's kinetic energy. So we might think, I want to do more, right? So we can turn up the intensity, and intensity is power per area or energy per time per area. So if we increase the rate at which we're doing this and really just ramp up the intensity, there's more energy available to knock these out. We start to see more photocurrent. More of these electrons just blow out. That's interesting. So do the same experiment, and if we do this with a different color, all right, so we're going to be loaded with electrons. And now we'll shine some red on it. And we're waiting, and we see nothing. Nothing happens. So there must be some kind of relationship between the color and the energy of the light, right? So the energy must be color dependent. So that's very strange that there's a frequency dependence on the energy. Because these could be at the same intensity, right, with the same amount of light being delivered, but for some reason blue works and red doesn't. So that's really weird. But not a big deal. Fine. Apparently there's not enough energy. So let's just turn up the intensity and add more energy, which we know how that works, and we still don't get anything to happen. So two things that come out of this experiment. The light energy relates to the frequency. It depends on color. And the second thing is, whatever this process is, it's all or none. I can't shine red light that's not energetic enough and just keep pumping it in there, right? And then save up until I can have enough to get out. It doesn't work like that. This isn't like pushing a rock up a hill, right? It either happens or it doesn't. So these two things together are really interesting. And this is the photoelectric effect. These two conditions, this tells us that the light is somehow frequency dependent, and this tells us that the light must kind of be concentrated. It's not a big spread out wave. It's more like a hard nugget. So when you have, say, a torrential rainstorm, much like the one that I had this morning, you look outside and it looks like just sheets of water. It looks like it's continuous. But if you get up really close and personal and look at it, you can see, oh no, it's not continuous water everywhere. It's concentrated into little tiny raindrops, right? And they're just showering at a high rate, right? That kind of gives you the impression, if you're too big, it looks like it's continuous. When you stand underneath a lamp, that's the exact same thing that's happening. You're being showered in these little particles of light, or these little quanta of light. and we call them photons. It's just a particle-like concentration, a little nugget or corpuscle of light. Okay, there are things that the light's energy relates to. Each individual photon carries its own amount of energy, and that's related to Planck's constant times the frequency, where Planck's constant is, I think, 6.636 times 10 to the minus 34 joules. That's a pain to use. Something that is a little bit better, at least for us, frequency is usually what we use to describe sound, but we usually talk about light in terms of its wavelength, right? So we could say, well, C is equal to lambda F, and translate this into this form. And I like it much better. Okay, what else is great about this? HC. I can treat this like one combined variable or combined constant. I already know these two values, so I can just multiply them and set that number aside for future reference. And when I do it, I get 1241 EVs times nanometers. And depending on your instructor, you might see it 1, 2, 3, 4 EV nanometers. It's just easier to remember, but it's a little slightly off. This is convenient because light is usually given in terms of nanometers. And an electron volt is a super convenient unit in atomic physics when the energies are really small. Answer me this. I have some amount of energy that an electron absorbs to do something. And let's say that the energy is, let's say it's 4 times 10 to the minus 19 joules. This is a real number. It's useful in calculations, but what does it mean to you? Like, does you, in your gut, do you feel 4 times 10 to the minus 19 joules and just intuitively know what it means? No, probably not. So we can say, well, what is the energy? From way back in the course, we learned that it was a charge times a change in a volts. Well, we know the charge is an electron charge, and the volts will be some number of volts. So if I divide out 1.6 times 10 to the minus 19 coulombs from this, I'll get, I think, 2.5, 8, 16, 24, 32, 40. Yeah. 2.5 times, let's say, joules per coulomb times 1.6 times 10 to the minus 19 coulombs. Well, this is a variable, so why don't we just call it 2.5 volts, joules per coulomb, times this value, which is an E, or we made up a unit out of laziness, 2.5 EVs. They're called literally electron volts. These are useful for me because I have a kind of an idea in my head about what this feels like for small energies. It's the amount of energy one electron would get if it fell through 2.5 volts of potential. And this is almost two regular alkaline AA batteries. So it's helpful, right? And then also, when you're dealing with these astronomically large or infinitesimally small numbers, they lose all their meaning. So this is nice because it kind of gets us back into, you know, whole numbers, or at least close to integers without super long decimal points. So that's just what an EV is. It's a useful unit that we use. We made it up because we're lazy, and we do it to give context. In much the same way, if I said, you know, what's 27 meters per second squared worth of acceleration? Well, I don't know, but I can say that it's kind of close to, what, about 30 Gs or so? You know, a G, what's a G? It's a unit, but it's literally gravity. 9.8 times 10, or 9.8 meters per second squared. So another case where we use that. All right, so we are now armed with this understanding. We know what EVs are. How do we do photoelectric effect problems? If you can count change, which some of you have probably never seen before, back in the good old days we used actual, like, physical money. We've got an electron that's trapped in a hole. And its depth is an energy depth that we call the work function. It's either W in your book or it might be phi. So the work function is just how deep are you, which you can think about it in some ways as like an MGH, right? You're in a hole. And we're going to define this to be energy is equal to 0. My electron right now is this goldfish cracker. And, well, it doesn't have a smiley face on him. Too bad. So he's stuck in prison saying, please help me. I need to get out. So we can buy its freedom. Let's say the work function is maybe 10 EVs. And I've got a photon that has 10 EVs worth of energy in it. So we'll make a trade. The photon comes in, interacts with the electron, is absorbed, and then gets it to freedom. There we go. You know, you're set. Okay, let's say instead of 10 EVs, we'll do 50 EVs. So if I were to, no, let's not make it 50. Let's make it 25. I'm going to commit. This work function is 25 EVs. So that means if we use a 25 EV piece, the quarter, it comes in, it's used, the goldfish cracker gets out. If we use 25 EVs and hit it with, say, a 10 EV instead, this isn't enough, right? 10 is less than 25. You don't have the energy to get this out. So what's that mean? The photon essentially doesn't interact at all. This entire situation is in some ways transparent to the photon, right? Won't be absorbed. This idea that, oh, well, I can just start banking these things doesn't really work. I can't take 2 of these plus, oh, I left my nickel inside, but, you know, I can throw all the change of this that I want. If it's not hard enough to get the goldfish out all at once, then it doesn't happen. Multiphoton interactions are possible, but the likelihood of them happening has to be exactly simultaneous, and it's kind of a rare occurrence, and it's something that you won't talk about until you get to physics 911. So we will assume that we only have single photon interactions. What if I did something like this? It's 25 EVs deep, but I paid with a photon that was too high. I put 50 EVs in, I get the electron out, but then there's 25 extra EVs left. And what do we do with those? We put them into this in the form of kinetic energy, and then the goldfish spins off, or the electron peels away with all that extra energy. So why do I say this is like counting money? If you have cash, it's equal to the price plus the change. What you pay with, we take away what it costs to get out, and then return what wasn't used. So the photoelectric effect formula, E photon, that's going to be equal to the work function plus the maximum possible kinetic energy that could come out. There it is. That's all there is to the photoelectric effect. What's your work function? Use something to pay it. This has to be greater to get any kind of results. Your KE max is the maximum possible energy you can get out. And realistically, this number will be a little bit less. There could be heat interactions, there could be other radiative forces, there could be other stuff going on that kind of takes a little bit of that KE out as a tax. But if you got 100% conversion, this is the highest number that you would get out. When we want to capture these things with the photocurrent device, we could in some way say, I want to make this come to rest, right? So my goldfish is spinning or speeding at some V with some kinetic energy, right? How many volts would I have to put on it to make it come to rest? And the question is, how high would it get if I put a bias on it before it reached rest up here? And then eventually, stopped and turned around. This value of PE needed to undo the KE in a separate problem is equal to Q times some change in voltage, right? And that's called the stopping voltage. How many volts high do you need to make a hill that would cause this goldfish to stop and then not proceed any further because it can't climb? So I think that covers pretty much everything about the photoelectric effect. Okay. Our new theory is color matters. If you can't get the HC over lambda to be equal to your W plus any excess EV stopping, and maybe we'll write that as the expanded form of that equation, then you won't have anything happen at all. And that would be called the cutoff wavelength or the cutoff frequency. Any frequency smaller than that, or conversely wavelengths too long, you won't get anything at all to happen, no matter what you do with the intensity. Okay, and is there anything else in that problem? I don't think so. I don't think there's anything else we can talk about. Don't let this be something that takes you out. It's a simple, kind of easy thing. So cutoff voltage or cutoff frequency and wavelength are a thing. The work function is your depth. Remember, there could be a stopping potential to kill off this excess KE. And the main idea is that this is a single action thing where we see a wave and it turns out, nope, it kind of looks a little bit like a particle after all. It's all or none. It's like a piñata, right? I can tap on it like this all day. It'll never break it open. I need to really come up and smash this thing with a high velocity hit to get it to crack open and release its candy.